Hi, I'm Kunkun. Thanks for listening my presentation. Today, I'm going to present our team recent work, Semantics-guided 3D body gesture synthesis. For this project, we propose a novel system to synthesize the motion from speech. First, we extract low-level audio and high-level contextualized word features. The low-level features are capturing the bits of speech, and the high-level features supposed to provide more understanding information about the content of speech. The extracted features will be sent to the motion generator and discriminator, which are trained in an adversarial setting. For the generator, we propose a novel stochasticity residual module for the vanilla fully connected networks, which is to enable the stochastic. Since the motion synthesis from speech is supposed to be a stochastic process, this means that given the same speech, human can produce a different gesture. We formalize this problem as an autoregressive task, making an assumption that the current frame not only matter with the recent speech, but also matter with the previous stack of motions. As we can see from the formula below, the model G takes the sequence of future audio A, words W, and the previous stack of poses Y as the input. Based on this information, the model will produce an ideal pose for the current frame. Then the generated motion is the stack of generated poses. Here, I will introduce about the workflow of our system. First, both the low-level and high-level features will be extracted from the raw audio waveform and the text. Then, the extracted features will be concatenated with the previous motion and sent to the generator to generate the desired pose. During training, the previous motion will be provided directly so that the training could be fully parallelized. Then we send a sequence of stacked poses to the discriminator and ask the discriminator to classify whether this is the real sequence or the generated sequences. In test time, we use the previous output poses as the previous motion. Also, the discriminator will be disabled since we don't really care about the discriminator in test time. For the feature extraction, we convert the raw audio waveform to the Mel spectrogram with 27 channels. For the words, we are using the state-of-the-art BERT model to extract or contextualize word features from the sentence. Then we reduce the original high dimension to 32 with PC dimensionality reduction approach. For simplicity, we synchronize the audio, word, and pose have the same time length. For those frames do not covered by a word, would be paired with a zero vector, so that the word can have a consistent size as the pose. After the feature is extracted, they are concatenated with the previous motion and sent to the generator. The generator composed of 3 parts: a fully connected layer with tangent activation function, a stack of the proposed stochastic residual modules, and the final fully connected layer. The first fully connected layer with tangent activation function is to rescale and encode the features. Then the rescale features will be sent to the stack of the proposed modules. Finally, the output of the final modules will send to the final fully connected layer and produce the desired pose. More specifically, our proposed stochastic residual module named as state regularized residual fully connected module. It has 4 components. The first component is the vanilla fully connected layer with sign activation function. Here, the output of this layer denoted as Zx. The second component is the learnable parameter. We call them states as. The third component is the Gumbel softmax, which is an approximation of the argmax operation. Here we use the output from the last layer and have a dot product with the states. Then we send the result to the Gumbel softmax and get a probability for selecting every state. In the equation, there is a symbol G in lowercase. This is Gumbel distribution, which is the stochastic coming from. After that, we get the probability for selecting the state. We can have a probability mixture of the state. Finally, we have a summation between the probability mixture and the output from the last layer. And we send the result to the next fully connected layer. Similar to the last fully connected layer, it also has the sign activation function. To train this system, we introduce 3 terms: gesture loss, entropy regularization, adversarial loss. Gesture loss is to learn the mapping from speech and previous motion to the current frame. The entropy regularization is to encourage the state selection distribution to be more uniform, which is equivalent to encourage the motion to be more diverse. Similar to other GANs framework, we also have the adversarial loss for training the system to encourage the motion to be more realistic. Then we combine all these terms together and optimize the objective function to get the generator. Now we are going to evaluate the training performance. According to the figure, the model with using sign activation function can overfit through the training set faster and better than using ReLU in terms of the gesture loss. Even we are not using the proposed module and GANs framework, it still learns faster and better than ReLU. In test time, our system can generate a diverse motion by given the same speech with different random seed. As shown in the figure, the coverage area of motion trajectory are different. This indicates that our generated motion could be diverse. This already verified that our proposed system is not a deterministic approach. It's a stochastic approach. Summary: using the sign activation function could converge faster and better than ReLU on the training set. Besides, the stochastic module can generate a diverse motion during the text time. However, according to the crowdsourced evaluation, our approach still has a large room to improve. In future, we may add more relevant features to improve the human likeness and appropriateness so that the generated motion could be more realistic. Thank you for listening.